Welcome back to VEX Isn't Scary. This is part 6, and we're going over a couple of extra things that you need to know. So with the first 5 parts, we covered sections of VEX. And that should give you a very good starting point to go and pursue other tutorials and start to play around with VEX. However, there are a lot of things that were left out, mostly because they didn't really fall into any of those categories, or they would have taken away from the main lessons of those tutorials. So before we begin on the actual VEX project, which takes place after this part, I would like to clarify a few things in VEX. Alright, so the first thing that I want to show you has to do with the flow of conditionals. So let's go ahead and just create an attribute wrangle. And I'll also scatter some points and put them into here. So just a grid, and I'll shrink it down, and a scatter, just like that. And now in this attribute wrangle, I'm going to do a few things. So in here, I'm just going to have an integer. So over here, I'll make an integer called int toggle, and toggle will be equal to a channel integer. So we can create our own one here. And I'll call that toggle. Then I'll say if toggle equals 1, then do something over here. Now, what I'd like to do is just change all the colors of all these points. So what I'm going to do is create a vector color over here and just make it equal to 1, 0, 0, right? Red. After all that code, I'm going to say v@cd equals color. If I apply and accept, it works as you'd expect. Now I'm going to create our little toggle over here. So now we have a toggle and we can access this if statement if we switch our toggle to 1, right? So inside of this toggle, we could change our color. So we could say color equals set and then give it a new value. So 0, 0, 1. Make it blue instead. Apply and accept. And now if we toggle, it switches to blue. Now, what happens if we decided that we would rather create our variable inside of this conditional? Well, we're going to have a bad time. So let me show you. Let's remove that over there and create our variable inside of this. Now, before I apply and accept and get the inevitable error, can you figure out why this would throw an error? This would throw an error because this condition isn't always true, right? And this is the case with all conditionals. Because the state of this conditional is not known, we can't create our variable in here and then use it outside. Because if toggle is, say, 0, then it'll skip this code. And then when we get here and we say v@cd equals color, color doesn't exist because we said only create color if toggle equals 1. So this is a bit of a logic thing. If you want your variables to be available outside of a conditional, then you should initialize them outside of your conditional. Now, this code would be perfectly fine if we did this instead, because now it's all inside of the conditional, right? So if toggle is 0, it won't run any of this code, which means it'll never look for color outside of the conditional, right? So it'll never break. And this is perfectly fine as well, right? Your toggle still works, but you can't have it outside like this because then it won't find this color because it exists in an uncertain state. And something interesting about this is that you can actually create a variable outside of here with the same name. You can create vector color over here and make it equal to some other value, 1, 0, 0, and you won't have a conflict because this one exists in the context of this conditional, whilst this one exists outside of the conditional. And so the reason that this is okay is because this vector color over here never escapes this conditional. So that means that we can have our own vector color outside of it. So just keep that in mind, that your variables work in a sort of hierarchy. Variables created can be used by conditionals underneath them, but variables created inside of conditionals can only be used inside the conditional. Okay, for this next part, we're going to hit 2 birds with 1 stone. And what we're going to be going over is the detail attribute. So I'm going to create a grid. And on this grid, increase rows and columns and feed it a mountain node. So we just got a little mountain node going and we can scatter some points. And, you know, we can do things like v@cd equals, and then give it some arbitrary value. And you end up with this. Now that works because we're running over points. We're setting each point to have this CD attribute. So in our geometry spreadsheet, under our point attributes, you can see that we have CD on every point. If we change this to detail, it'll no longer be a point attribute, it'll now be a detail attribute. So under detail, we now have CD. But something interesting is that if we go back to our scene view, our points will still keep that value. And that's because if there is a CD attribute, and it happens to be a detail attribute, Houdini will still use that for your points. But points still take priority. So if your points have a CD attribute, Houdini will give that preference. So if there is no point attribute and only a detail attribute, it'll use the detail. If, however, there is a CD attribute for points, it will override the detail value. Okay, now that's one thing, but that doesn't explain why detail is useful in any way. So let's create a bit of code. Let's imagine that these are trees, and we have scattered it on our terrain, and we want them to be different colors depending on the season. Now, the season is something that sort of exists outside of the geometry, right? Even if this geometry wasn't there, those seasons would still exist. So what we can actually do is create an attribute wrangle and run it over detail and use that to control our seasons. So let's just Alt-E to bring this up. If you've coded before in another language, you'll probably know this as a switch case, but in Houdini, there isn't a switch case, so you use the else if. So for everyone else, I'll explain that very shortly. To begin with, let's create an int called season num, and we'll make that equal to a channel integer over here. And we can just call this season, right? Then we can create a string called season string, and we won't give it a value just yet. Next, we'll say if season num equals 0, then make season string equal to summer. Okay, so very simple. If this is equal to 0, then season string will be summer, right? It'll return summer. So what about the other cases? If it's a value of 1, you want it to be a different season. So that's where you use else if. Now, else if works like an if statement. You can say in here, season num equals 1, then do some other code. And in here, you would say season string equals, and then let's just make this one autumn. And then you can do it again. You can say else if season num equals 2, then the season string should be equal to winter. And then you can say else if season num equals 3, then just make season string equal to spring. Now, the reason we've used this else if is because we want to add one last else at the end. And this else over here catches everything else, right? So if none of these are met, then catch this. And of course, that would just be something like, if it's any other season, then just make season string default to something like summer, right? If it's a number greater than 3 or less than 0, just default to summer. And now you might be asking, why can't you just use if statements? Why can't we just do this, right? If, and else. And the reason is because of this last section over here. When we say if season number equals 3, then season equals spring, it will hit this else and it will make it summer, right? So only 3 will work because it's saying if season is 3, make it spring, but if it's anything else, then make it summer. So it actually ignores everything before it because this is the last one to run, and then it's saying if it's anything else, just make it summer. So the else if actually avoids that for us because the else if treats all of these that come before this final else as a single conditional. Okay, so that's just something about cases and else if. Then finally, we can create an attribute, s@, because we want it to be a string. So we use s@, call it season, and we'll make it equal to season string. Apply and accept. Now, if we create our little spare parameter at the bottom, we can go over to our geometry spreadsheet, and you can see that our season is summer. If we change it to 1, our season's autumn. Change it to 2, season is winter. Change it to 3, season is spring. Anything else, it defaults back to summer. The cool thing about that is once you have this in place, you can drop another attribute wrangle, and this one can run over your points. And in here, you can call upon that detail attribute. So let's use a variable in here, and we can call this just something like string found season equals, and we'll make it equal to that detail attribute. So we have to use the detail function because now we're working with points. So we can't say something like @season, because it will look for @season as a point attribute. But we know that this is a detail attribute that we created. So we say detail, 0, comma, and in here we look for season. So now it's looking for a detail attribute in the first input called season. And so that should find our detail attribute for us. And then we can use that detail attribute. We can say if found season equals summer, and sorry, that's equals, or found season equals spring, then make all of our trees green. So make our v@cd attribute equal to green, so 0, 1, 0. And we can do a separate if statement just saying if found season equals winter, or found season equals autumn, then make our color red. Maybe we'll do something like orange. Now if we apply and accept, if we change our season on our season wrangle, so let's call this our seasons, and let's just call this our tree color. So now we can check all of our different conditions. If it's summer, then the tree should be green. If it's autumn, they should be orange. If it's winter, they should be orange. And if it's spring, they should be green. And that's pretty cool, right? It's using that detail attribute. The cool thing is this is completely independent of geometry. So we can use this in interesting ways. So if we delete all points, so let's just delete all points over here, and then happen to add another point from another input. So let's just add a single point. This point will still follow these rules because seasons is independent of geometry. So even when we delete all of our points, detail still exists. The season still exists. And that's how it works in real life. The seasons are independent of the trees. And, there's other ways to use this that's also quite interesting. For example, if instead of plugging it into first input like this, you can have this as a separate thing where you just feed in the seasons. And all you have to do is say, instead of getting it from the first input, get it from the second input, and it still works, right? And this is what makes it so powerful, is that this can be a standalone node that just controls seasons. And so you can do incredibly powerful things with detail attributes because they don't rely on geometry. Next, we're discussing something that you've used before, but might not have known what they're called. And these are common attributes. So I'm going to drop down a geometry node right over here, dive inside and drop down an attribute wrangle and just something like a sphere. So I'm going to change this to a Polygon Mesh. And in this attribute wrangle, I'm just going to do something very simple that I'm sure you've seen before. v@p.y plus equals 0.5. And that will move every point up by 0.5. And we can also do something like v@cd equals 0, 0, 1. And that will make our sphere blue, right? Every point is blue and every point has been moved up by 0.5. Now, why does that happen with those two attributes, but not with something like if we had to do v@position plus equals 0.5, right? So why does v@p.y work, and why does v@position.y not work? And this is because of something known as common attributes. In Houdini, there are attributes that are recognized by the software, and this makes things a lot easier for us because it can control aspects of our geometry or rendering simply by us changing those attributes. And so we've already used v@p, v@cd, but there are a bunch of other ones, and it is important to know them, or at least to know most of them to avoid naming conflicts. When I started in Houdini, I wanted to create an attribute that defined the y-axis velocity, and I called it up, and things broke. And things broke because @up is one of those common attributes. And there's a bunch of other ones, there's @up, @n, @p-scale, @force, @rest, @orient, @v, but there's something that you'll notice about all of them. They're not particularly descriptive. They're all very straightforward names. And so to avoid a naming conflict, just try to use descriptive names. For example, we know that v@v is for velocity. So you could name your attribute @velocity to avoid a conflict with @v, but even better would be to name it something like @custom velocity. Things like that ensure that your code doesn't have any conflicts. And so here are a few common attributes that I use often and a quick description of them. So v@v, as I just mentioned, is the velocity attribute. So you can give a velocity as a vector. So let's do 0, 10, 0. And if you take a look at your point trails, you'll notice that there are trails pointing down. That is because this sphere is technically moving up. That's what velocity represents. And you can feed this into dynamics networks. Oftentimes, a dynamics network can pick up your velocity attribute and use that as initial velocity. So for example, if you were creating a cannonball and you wanted to shoot it out of a cannon, you could give it some initial velocity with v at v, right? And when it gets put into the dynamics network, it will use that velocity and shoot the cannonball out. Another thing that this allows is motion blur. So if we very quickly go over to our render tab on our node, go over to sampling and switch on velocity blur, and then just create a mantra render node. And on the mantra render node, go over to rendering and allow motion blur and give this a quick render. You'll notice that there is some vertical motion blur, and that's because of our V attribute, our velocity attribute. And you can add velocity on another axis. And as you can see, that gives it a diagonal velocity because it is 10 on Y and 10 on X. So it averages out to a diagonal velocity. Now, there are loads of other common attributes. And the next one that I want to bring up is p-scale. So let's scatter some points onto our sphere. And over here on our attribute wrangle, we'll randomize p-scale. So we'll say at p-scale equals rand at pt_num. And you won't notice any change right now. But if we decide to copy 2 points, plug this into the second input, and then just add a cube to first input, when we copy 2 points, each one will have a random scale. So I'm going to just multiply our p-scale by 0.1. As you can see, each cube now has a random scale. And this is a uniform scale. So it's the equivalent of changing this uniform scale on your box node. You could use at scale, which is another common attribute, which is a vector, so it's v at scale. And this one can actually change the different components of the vector. So you can have v at scale dot y equals 1. And now you can see that each one has a scale of 1 on the y-axis, but a randomized scale on all the other axes. Okay, so we know that that works. But now that we're looking at the orientation of our cubes, it would be better if, say, they were oriented onto our sphere's faces. So if we drop down a normal node and feed it in before the scatter, you'll notice that it orients all of our cubes to sit on the face of our sphere. And the reason is our sphere picks up these normals, and when we scatter, that gets transferred onto our scatter points. And normals are one of the orientation attributes. So by default, Houdini will use normals to orient all of these cubes. Now there are other orient attributes, such as the orient attribute at orient. Now this one is a bit more complicated, and we do touch on it in the VEX Isn't Scary project, so we'll be touching on that soon. But for now, just keep in mind that normals are another common attribute that Houdini recognizes, and they are represented by v at n. So another thing that is kind of interesting is if we drop down a delete node, right, and we decide that we're going to delete some points, and we're going to delete by range, and we'll just delete a random number of points each time. As you can see, each time we delete a point, the scales of these all change, right? And the reason is because in our rand over here, what we're feeding in is at pt_num. Now, at pt_num is what is known as an indexing variable. There are a couple of other ones, such as at prim_num, which is the equivalent for primitives. There's also at vertex_num, at element_num, or elem_num. But then there's also at num_pt, which is the total number of points. And at num_pt, if you have 1,000 points, at num_pt will return 1,000. But getting back to what we were saying, when we delete points, our scales all change. And that's because we're using at pt_num as a seed for rand. So when our number of points changes, all of the point numbers change, and all of their scales change because of it. So a good practice, and this is something that you'll probably do quite often, is to add an ID attribute. And this is something that the PopNet adds for you. It adds an ID attribute, as well as some other dynamics networks like the flip solver. It adds an ID attribute for you as well. But ID is another common attribute that we can actually create as well. We can say at ID equals at pt_num. And we create it over here because we know that each point number is unique at this point, right? So if we take a look, at ID is equal to each point number. And there's no overlap, right? It's all unique. Then when we start deleting points, so if we delete a bunch of points, you'll see that our IDs remain from before, right? Our IDs don't change. The point numbers do change. So what this allows is for us to replace @ptnum with @id, and this is constant for each point. So now if we delete points, their scales stay the same, right? There's no changing scale. All of the scales are based on a constant, unique identifier for that point. So if you want to learn more about common attributes and indexing variables, you can actually go to the documentation. It is sidefx.com/docs/Houdini/model/attributes. Now, I know nobody actually enjoys going and reading through documentation, so if you want, you can, but I wouldn't recommend it. I'd say to just know these few that I've shown you, because these are probably the most useful ones. So just know that there are a lot of common attributes that Houdini does recognize. So just know that to avoid naming conflicts, and always name your variables in a very descriptive manner. So that's all for this in-between part. In the next part, we're starting on the VEX Isn't Scary project, and we're creating a pretty cool effect based on the to-see couple and simple harmonic motion. It's going to be really cool, so I hope to see you there. Bye.